Okay, hello everyone. Welcome to week 7 of my exploration of the big book, A New Kind of Science. And this is in celebration of the 20th anniversary of New Kind of Science, which is coming up on May 14th of this year. I've been going through successive chapters of the book. And today we're going to talk about chapter 7, which is called Mechanisms in Programs and Nature. And we're just over halfway through the chapters in the book, and let me show you. There we go. So the chapters between 2 and 6 have really been laying the groundwork for what kinds of things are out there in the computational universe. Abstractly, what kinds of simple programs are there and what do they do? What we would now call ruleology. It's been an adventure and an exploration of ruleology, kind of the core ideas of ruleology. The next few chapters, well, particularly 7, 8, and 9, have to do with relating the things that we've discovered ruleologically in the abstract world of simple programs with things that exist in the real world and in nature, connecting those kinds of things. And so chapter 7 begins that process of connecting the abstraction of simple programs with the reality of things in nature. So if we look at chapter 7, we'll be talking about several different kinds of things. There was quite a lot on randomness and the question of randomness. And then there are things on other kind of core features of phenomena that we see in the natural world. So the chapter begins by talking about the universality of behavior, the question of whether it is the case that the things that we've seen in simple programs are kind of strong enough phenomena that they will be universal, not only across simple programs, but also across systems in nature. This theme will be picked up more strongly in chapter 12 when we talk about the principle of computational equivalence, which is kind of the big principle that came out of A New Kind of Science, the book, and that has been kind of a guiding force in a lot of the science that I've done and many other people have done in the years since then. But in chapter 7, we're kind of doing the early run-up to that, having observed that when we look at simple programs in the computational universe, there are phenomena that are quite universal across many kinds of programs. For example, the very core phenomenon of even though the rule for the program is simple, the behavior that it generates may be very complicated. That's a phenomenon that is strong enough, it's universal across a lot of simple programs, and we might imagine it will be universal across also systems in nature. Okay, so the first big phenomenon that we talk about is this idea of randomness. And maybe I should just look at down here at the notes. I'm trying to remember what notes there were. Okay, yeah, this is talking about the history of this question about sort of the universality of phenomena. This idea that there can be there can be sort of similarities between, for example, the physical world and the biological world. The kind of thing that Darcy Thompson had talked about, the kind of thing that was talked about in connection with fractals and so on. The kind of thing where, in a sense, mathematical models have this feature that they often have the same mathematical structure, but nevertheless address different kinds of systems. All right, but the first big phenomenon that we talk about here is the phenomenon of randomness. And so one of the things I observe here, single most common things one sees in nature is apparent randomness. And the question is, does all the randomness that one sees in nature come from the same source or not? And one of the important things that I did here, which I had actually done previously I'd sort of started this in a paper that I wrote in 1985 or so called Origins of Randomness in Physical Systems. I tried to identify what are the core essential phenomena responsible for randomness. In a sense, what is the appropriate meta model for the phenomenon of randomness? Not necessarily a specific model for a particular kind of system, but rather kind of a meta model of what is the core phenomenon that's leading to randomness. Now, I have to say that people get unbelievably confused about this. I mean, even amusingly, within the last week, I saw a long description and question to me that was essentially a confusion about this very issue. So let me try and explain this, as I think I explained it fairly clearly in the NKS book, but let me try and explain this a little bit here. So there are three fundamental mechanisms that I think one can identify for where randomness comes from. So we're looking here, this left-hand column this is what we observe. This is a sequence of, let's say, ones and zeros, data, whatever it is that's coming in, and it looks kind of random to us. How does it come to be that way? One possibility is that the thing we're seeing here is really a reflection of the environment in which the system we're studying is embedded. And so in a sense, there's randomness raining down on our system from the environment. So every pixel, let's say, in our system is being independently kicked around by this randomness from the environment. So in other words, what we see as the output here is really a reflection of aspects of the environment for the system. It's not an intrinsic feature of the system, it is a feature of the environment of the system. So that's case number one. Case number two is randomness from initial conditions. The system itself, in this case, is just shifting bits one position to the left. So it, in a sense, doesn't generate any randomness itself, but the initial conditions for the system, if they're random, then the behavior of the system will gradually deliver the randomness that was in the initial conditions, will gradually deliver it to the thing that we're observing. And so that's kind of a second mechanism for randomness, is randomness from initial conditions. The third mechanism, which is the mechanism that really we discovered in NKS, is intrinsic generation of randomness. The idea that randomness can be produced not from the initial conditions, not from the environment, but intrinsically from the rules for the system itself. It can be intrinsically and computationally generated. Now, in a sense, this is not a surprising thing. Something like the digits of pi, we're quite used to the idea that there's a definite rule for producing them, yet once produced, they seem for all practical purposes random. But the fact that that could be a thing that generically occurs in nature, that's a thing that the NKS book really emphasized and really introduced. And so Rule 30 is sort of the quintessential example of that phenomenon: simple rule, simple initial conditions, yet intrinsically generating randomness in the behavior. All right, so those are the three basic mechanisms for randomness. And what we're going to do here is look at those different mechanisms for randomness and ask and talk about them. So for example, when you see something random, so you're on a beach, you're looking at the waves coming in, and you see that they come in a kind of random way. How does that come to be? Well, there's some, it's something that can be from the environment. It can be a storm. It might be 100 miles away, and gradually those waves have come to shore and you're getting to see them. But the basic point is that there is randomness from the environment, and you are seeing but a reflection of that randomness from the environment. Brownian motion, another good example I mentioned here of randomness from the environment, where you have a pollen grain and you've got it in water, let's say, and there are actual molecules buffeting it, and the random motion of the molecules, which is sort of the environment of the pollen grain, kicks the pollen grain around in this seemingly random way. So let's see, in something like radio receiver, this is something that's becoming perhaps increasingly outdated by the advance of technology, even in 20 years, that this is about an analog radio receiver where you tune the radio receiver between radio stations. I'm not even sure you can do that anymore. You're just typing in digital data, or you're specifying a radio in some software level way. But in any case, let's say that you're just tuning your radio to between radio stations and you hear this noise. Well, what's happening is that the radio receiver is amplifying something that isn't really there. It's amplifying the noise in the system. It's amplifying thermal noise. It's amplifying it's amplifying kind of the electronic noise that is a result of random thermal processes, random molecules bouncing around in different configurations that are essentially the environment, the heat bath of the system. I talk here about a bunch of other examples that are talking about some spark gaps, other kinds of things here. I talk about the fact that in these situations where you think you're just seeing randomness from the environment, even that you actually don't get very good randomness in many cases, because the effects of the system, like you have a spark gap, you have there's breakdown in the air, for example, between the two plates, and then it takes a while for all the ions that were produced by doing that to clear out before you can again have sort of an unbiased, statistically independent spark produced. Okay, so that was sort of a survey of randomness. Let me see here, randomness from the environment, and there are a variety of kinds of situations. I talk about actual randomness, different section on ocean surfaces, electronic noise, the details of how you actually get electronic noise. Actually, it's interesting, in 20 years, I say that a single bit of data is represented by 10,000 electrons. It's still about 10,000 electrons, but I say that as an example, but that's about the number between 10,000 and 100,000 electrons. I talk about mechanical randomness from shaking and stirring and so on. And the fact that there is, even when you have a bunch of balls bouncing randomly around, it takes a long time for correlations between those balls to disappear. I mentioned here, I don't know if it's still the case 20 years later, all the state lotteries in the US are currently based on mixing between 10 and 54 balls that, I don't know whether they still show that stuff on television and so on. But other sources of randomness that were used were things like digits and financial data in newspapers and so on. Those are just sort of interesting sources of randomness. I think I cataloged different kinds of sources for randomness. There's been a little bit more developed technologically since then. In computers, talking about timing information and so on as a source of essentially randomness from the environment. And talking about the fact that in most randomness from the environment, it's very non-reproducible. That is, the heat won't be the same every time you run it. Now, there's sort of notions that have arisen in intermediate years, physically unique functions and things where it depends on sort of the way that a particular piece of a circuit was produced when it was manufactured and so on, and that can be a thing that was in a sense in the environment when it was manufactured, but then it is fixed after that. What did I have to say about randomness in biology? I'm talking about here, thermal fluctuations and chemical reactions lead to all sorts of microscopic randomness in biological systems. Randomness in embryos can affect pigmentation patterns. Random changes in DNA can have effects. All sorts of details here. Right, this is the randomness in the immune system when antibodies are formed. These are pieces of these are randomness that come from thermal fluctuations and chemical reactions. And I mentioned animal behavior controlled by electrical activity in nerve cells. And again, there can be randomness in that. Again, this is essentially all randomness from the environment. Okay, part 2 here is randomness, chaos theory, and randomness from initial conditions. So this is a different idea for where randomness comes from, and let's talk about that. So I talk about, well, the sort of first example that I give here is flipping a coin, or spinning a wheel, which is spinning something which is black for one hemisphere and white for the other hemisphere. And you spin it and you ask which way it's going to come up. Well, once it's spun and it's spinning, it's completely determined. What determines which way up it lands is what the initial velocity was. Because here we're showing the slowing down of the disk, and we're showing that if the thing comes to rest in this section here, it will be white on top. If it comes to rest in this section here, it'll be black on top, and so on. And what this picture shows is that the question of which way it will come up depends sensitively on what the precise velocity was when you started it off. And that's where the randomness of coin flipping comes from. It's not something to do with the coin itself. It's something to do with the fact that when you flip the coin, you're not determining precisely. Your nerves are just only approximately determining the speed of the coin. But depending on the precise details of that speed, you'll end up coming up with a different result. And so that's an example of randomness for initial conditions. It's randomness from the initial velocity, but once the coin is in motion, so to speak, everything is determined. Well, let's see. This is let's see if I have a picture here. Here we go. So this is another example of randomness for initial conditions. This is kind of a kneading process where you're taking points and you're making the points always, oh, here I show how it works. So you're basically, you have a bunch of initial points, you have some dough, for example, and at every step, you're stretching the thing out by a factor of 2, you're cutting it, and you're putting it on top of where it was before. So that means that 2 points that are nearby initially will gradually be stretched out, and eventually they'll land up in a different slice here, because eventually, if they, depending on precisely where they were in the initial conditions, they'll end up being to the left or to the right, and then their placement will be determined by where they were initially, but in a somewhat complicated way. Well, if we look at that in terms of digit sequences, here's what we'll see. What's happening is we start off with some initial number, and that initial number, we write it out, let's say in binary, that will correspond to that kneading process I just showed before. And at every step, the positions of points will be essentially gotten by doubling and chopping off the top digit. So we're essentially shifting everything 1 digit position to the left. So what's happening is, as if we say, well, what does the system do? What's the value that we get after 10 steps, for example? Well, that will be a reflection of whatever the 10th digit was. What about after 1,000,000 steps? Well, it'll be a reflection of the 1,000,000th digit. So now the idea is, well, how would we know what that 1,000,000 digit is? In a system, we will typically not know. We'll just be picking, for example, in standard mathematics, when we think about real numbers, it's like there's a whole infinite collection of numbers in the interval 0 to 1. Which one do we pick? And do we pick one whose 1,000,000th digit has some particular form, whose 1,000,001st digit has some particular form? No, we imagine in typical mathematics, we're just picking a number by its value at random. And so it'll have a sequence of digits that will be random and that we will progressively excavate as we do this shifting. And so that means that, again, we've burnt in the randomness from the beginning. There's no randomness in the shifting process. It's all burnt in the beginning. And we have this idea that for some reason, we're going to pick those initial conditions at random. For example, when we're flipping the coin or whatever else. Now, this phenomenon became almost mystical at various points. And it sort of became this idea of chaos theory. And it was very confusing because people said, oh, chaos, that's where randomness comes from. But it's simply not true most of the time. Most of the time, this phenomenon that you have, that you've just got randomness in the initial conditions, and then you're progressively amplifying it, that's not what's going on. It's either randomness from the environment, or, as we'll later talk about, it's intrinsic randomness generation from things like rule 30 or the digits of pi. But chaos theory was have been very famous, and it's something that I wanted to try and clarify in the book, how it related to what I'm talking about. So let me try and invent some systems where you can sort of see chaos theory in action. Here's a system that involves an arrangement of mirrors. And this arrangement of mirrors is such that when light bounces off these mirrors, the mirrors are arranged to be somewhat convex here. So that means when light comes in a particular, when 2 light rays are nearby, because of the convexity of this mirror, they'll be reflected to be at different angles, and so they'll be further apart. And so what happens in this particular picture is one's got this kind of elaborate system that's bouncing light rays, and 2 light rays that are just a tiny distance apart here will progressively bounce to be further and further apart. So in this particular case, the position of the initial light rays is given by pi/4, which is some digit sequence here. And what this thing is doing, this is essentially an optical analyzer of numbers. And it's basically excavating the digits in that initial number. And the way these bounces go will be determined. This thing is set up to basically bounce according to the progressive digits in this number. So it's a slightly put up job. It's a slightly, this is a slightly elaborate system. It's not something you would naturally find sort of lying around in nature. And in fact, that's a general feature of this phenomenon of sensory dependence on initial conditions. You have to have a system that has a sort of instability in how it's behaving. And most systems, by the time they've been running for a while, they no longer have an instability. They are just doing what they do. But you can certainly set systems up to have these instabilities. Here's another example. This is a pegboard where you are dropping balls on the pegboard. And because the pegs are circular, the balls are bouncing off at angles. So as soon as the ball hits a little bit off center, it will be bouncing at a larger angle than it came in at. So in other words, if it's right on center, it will just bounce back straight up. But as soon as it's off center at all, it will be sent further to the left or further to the right than it was before. And so what we see here is a few balls started off very nearby, which now, because their initial conditions weren't precisely the same, progressively, this is excavating the digits in those initial conditions, and you see these very different trajectories that result. Now, in practice, you can't make this a device like this as all that accurately, and so these trajectories won't really correctly reflect the 50th digit. They won't even probably reflect the 5th digit in that initial number. They will be reflecting other features of this system. Well, so it's actually pretty hard to find a case where you can actually have really accurate kind of sensory dependence on initial conditions. One of the few cases where you get this to maybe 10, 12 digits, something like that, is in celestial mechanics, in the motion of planets and so on. And so this is an example from the three-body problem. It's kind of an interesting example in many ways of the three-body problem. Is a problem of, let's say, Earth, Moon, Sun, each gravitationally attracted to the other, but moving according to laws of mechanics. And then you ask the question, well, if you set these things off in different initial configurations, what will be the behavior? And the answer is the behavior can be very complicated. But the behavior depends only on that initial condition. You change the initial condition, you determine the behavior. Now, it's a little bit confusing because some aspects of this behavior are a little bit more like intrinsic generation of randomness. But at least we can ask the question, is there sensory dependence on initial conditions? Is it the case that when you just start the moon off in a slightly different place, what will happen? So this is an example, which is a very nice minimal three-body problem. This imagines that you have two stars that are in orbit around each other, and they're in a plane. And then there's a planet or a star of essentially zero mass that bounces up and down through the plane of those two stars. And exactly how much it bounces and how this works will depend on exactly in what phase the main stars were when it went through their plane. And what this is showing is that if you start off with several different initial conditions that were just a tiny bit different, after a little while, you'll end up with completely different behavior here. Now, this is a tricky thing to compute. This was certainly done in Wolfram Language and Mathematica, where we have arbitrary precision arithmetic, where we can actually keep track of 100 digits, 1,000 digits, or whatever precision, and we don't kind of lose information from our numerical computation. So this is one of the sort of few cases where you can sort of genuinely see sensitive dependence on initial conditions. Okay, so there are a bunch of notes, I think, in this section about all sorts of different things. Okay, so this is spinning and tossing as sources of randomness. That's the mathematics of that. I talk a bit about billiards and the fact that if you have a billiard table with where the sort of very precise angles that you use, you can again get this kind of excavation of initial data in the way the bounces work. I talk a bit about fluttering, the fact that pieces of paper sort of seen fluttering, and I apparently mentioned by James Clerk Maxwell in the 1850s. I actually comment here that this is probably not an example of sensitive dependence on initial conditions, but rather an example of intrinsic randomness generation. Okay, I talk a bit about the history of chaos theory. It got very confused because it got very kind of promoted in the 1980s. The idea that small causes can have large effects is something that people have talked about forever. In things like, for want of a nail, ... For want of a nail, a horse was lost. For want of a horse, a battle was lost. For want of a battle, a kingdom was lost, type thing. Small causes can have large effects. James Clerk Maxwell, again, noted this phenomenon of sort of bouncing balls and the fact that small changes can yield randomness in gases. I didn't actually remember this point, that in the 1870s, Maxwell suggested mechanical instability and amplification of infinitely small changes at occasional critical points might explain apparent free will. That's an interesting and prescient, although I think ultimately not correct, explanation for that phenomenon. 1890s, Henri Poincaré was famous for having studied, he started off studying the three-body problem, ended up studying more generally kind of surfaces of constant negative curvature, things like this, places where trajectories diverge. And a variety of other people studied that. 1927, Van der Pol, that was a time when radio receivers had started to exist and there were started to be radio amplifiers. And one of the things one could do is amplify nothing. And one could say, is one going to get a kind of noisy behavior when one has, let's say, a vacuum tube amplifier? And Van der Pol wrote down a nonlinear differential equation, and then one started to be able to characterize the fact that in that nonlinear partial differential equation, a nonlinear ordinary differential equation, which, by the way, might not be a perfect representation of the natural system, but was at least a model of it, you could ask, was there sensitive dependence on initial conditions, in the sense that changes in the initial conditions for that differential equation would lead to large changes in behavior? And Mary Cartwright, John Littlewood, noted that was a phenomenon that Van der Pol's equation could sort of exhibit solutions that were sensitive to all digits in the initial conditions. Also iterated maps. Then, particularly famously, Ed Lorenz, who I knew somewhat, was a meteorologist, did a simulation of a simplified version of the equations for airflow in the atmosphere, and showed that in those particular equations, there was this phenomenon of sensitive dependence on initial conditions. Now, in the end, and Ed Lorenz certainly agreed with this, it was a bit of a put-up job, because in the true atmosphere, there is viscosity, essentially friction in the air, that damps out small effects. And what Lorenz did was he used a truncation of the equations that ignored viscosity. And so, in a sense, the Lorenz equations are only sort of sensitive when they are right at the edge, right at some point of bifurcation, right when it was, just between a high pressure zone and a low pressure zone being produced, or some such other thing, or something a lot less global in the actual equations, right at that knife edge. That's where there could be sensitive dependence on initial conditions in a real system like that. Most of the time, the dependence on initial conditions will be damped out by viscosity. But that was something that was sort of very famous in launching what became the idea of chaos theory. And people talked about, how the flapping of a butterfly wing might change the weather, might make a hurricane happen in some particular place, which is basically nonsense. There is a knife edge moment where, if you picked a quadrillion butterflies, one of them might have that property. But the generic butterfly is not going to have that effect on history, so to speak. Now, it is the case that if you look at initial conditions for some simulation of weather or climate or whatever else, it is true that when you look at those simulations and you change the initial data that you give to those simulations, you will change the output. But many aspects of the output are not changed by changes in the initial conditions. And the sort of dramatic change from an infinitesimally small change in initial conditions is very rare. So a bunch of mathematical studies got done, and in it kind of became a scientific concept by the early 1980s that, chaos was going to explain randomness in nature, that randomness in nature was the result of sensitive dependence on initial conditions, and it's basically almost never true. So, okay, we're talking here about instabilities, and the talk here about the three-body problem, and the three-body problem, I think, has a lot more mileage to be got, not so much from this question of sensitive dependence on initial conditions, but from the question of what can you compute with the three-body problem. And it is my strong suspicion that the three-body problem is actually capable of computation universality, that with appropriate initial conditions, you can have it compute anything that a computer can compute. But that's tricky to deal with because these initial conditions are stated in terms of real numbers, and it's very easy to sort of confuse yourself because an ordinary computer has only a finite program, but a real number has an infinite number of digits. Even though you might not be able to actually prepare that infinite number of digits in any finite way, in principle, it has an infinite number of digits, and untangling what's the result of actual dynamics of the system versus what did you pack into the initial data can be a tricky thing to do. But if we look at the three-body problem, these are examples of what happens as you change the parameters of the three-body problem, starting. So sometimes you'll get the bodies will just, two of them will just form a close orbit and the other one will go off to infinity. But very often you have these tangles that last for a long period of time, where it's a kind of like undecidability staring you in the face, because it's like, what will be the outcome from this computation that is the three-body problem? Well, you can't tell. It's all tangled around for a long time. So let's see, I think maybe I had another, yes, here we go. So this is the simple case of the three-body problem that I illustrated in that picture. Oh, wow, there's a typo in the online book here. That should be a differential D, not a delta. It's kind of disappointing. So in any case, this was a particular example of the three-body problem that was really reduced to this differential equation. It's just an ordinary differential equation here, as is typical in three-body problem. It's an ordinary differential equation, but it involves just one variable here. It's a kind of a nonlinear equation, and here we can look at, these are actual pictures of the dependence of the final result as a function, or the result as a function of time on the initial condition. So we see here, this is, as time goes on, for very early times, you don't see any difference. But here, zoomed in on Z0 between 1 and 1.1, you see all this kind of wild stuff going on. So you see that a tiny change in Z0 eventually manifests itself in a large change in the actual behavior of the three-body system. So I talk here about randomness in the solar system and the fact that there are actually cases where one can see a sort of apparent randomness in the behavior of certain asteroids and so on. I think more has been figured out since 20 years ago about that question. And there are indeed cases of, randomness in real systems in celestial mechanics. Okay, well, having looked at that, we get to talk about the big new mechanism for randomness that NKS really, introduced. It had been sort of talked about in that earlier paper of mine from 1985. So this is the story, rule 30. There is no randomness in the initial conditions, but there is intrinsically generated randomness in the actual behavior of the system. Now, people can immediately get confused. They say, what do you mean there's no randomness in the initial condition? That initial condition is just some number. It's as good as any other number. But the whole point is we have to imagine sort of a mechanical process for producing the initial condition. And it's very easy to imagine one that requires very few steps, that produces something that has a 1 in the middle and a bunch of zeros outside. But if we say we're going to fill in every digit here, we're going to very carefully fill it in, that takes lots of computational effort to do. So I talk here about the notion of sort of randomness and what we mean by randomness, and I talk about, for example, ways that randomness is made on computers. These are linear congruential random number generators, an early approach to making deterministic randomness on a computer. Talk a bit about how those work. Talk a bit about the fact that because these things are generating randomness by some deterministic process, eventually there will be some way that you can see that it is deterministic. One way you could see is just by saying, does it run the same way every time? Or can we see detailed effects of the underlying rules? If this was randomness from the environment, well, we'd have to know all about the whole environment to know what the next digit would be. Usually in intrinsic randomness generation, the point is that in Rule 30, we have this phenomenon that I'll talk about later in the book of computational irreducibility that means that there really isn't a way to tell sort of what the next digit is more efficiently than just by running the system for that number of steps. But there are sort of some junior examples of computational, of intrinsic randomness generation where you can start to tell. And I talk about this example of linear congruential random number generators as an example of that. So there's a lot said here about about processes of amplification and their comparison to intrinsic randomness generation. And essentially, what I'm saying here is these are, okay, so this is just asking the question, how robust is the intrinsically random sequence that we get here? If we make changes to the initial conditions, does it change the sequence? Or on this next page, if we make perturbations, if we just start randomly kicking, having the environment effectively randomly kick the system, will that have an effect on this intrinsically generated randomness? And the answer is eventually it will have some effect. There's often phase transitions where it discretely starts to have an effect, but the phenomenon is often robust with respect to some amount of randomness, some amount of externally induced randomness, some amount of randomness from the environment. Still, one is getting this sort of robust intrinsic randomness generation. So what are the consequences? So there are a few things to say about intrinsic randomness generation. There's a sort of a big point, which is the notion of algorithmic randomness and its relationship to intrinsic randomness generation. I talk here about various other random number generators, practical random number generators used on computers, which are examples of intrinsic randomness generation. Linear feedback shift registers are like additive cellular automata, different kinds of random number generators used on computers. I talk about things like card shuffling, which is, again, a very simple sort of intrinsic randomness generation process. But one of the things that's important here is I talk about algorithmic randomness. And okay, I talk about it in more detail here. Here's the issue. The issue is, in something like Rule 30, we are generating randomness from a simple initial condition. In some sense, we can say, oh, that sequence in the middle isn't random, it's just the center column of Rule 30. And we can give a description of that center column. It's quite short. Or it's like, that's just the digits of pi. Even though once generated, those digits are very long and it's hard to tell what the next digit will be, if we just are going to describe how to generate them, there's a very short way to describe how to generate them. So it's a big question whether there's sort of a definition of randomness that says something is random only if the shortest description of it is about as long as the thing itself. So that means there's no procedural rule for generating the thing. It is merely that you just have to say the thing. That's a little different from computational irreducibility. Computational irreducibility says there's a short description of how to generate the thing, but the process of generating it is something that you can't shortcut. Algorithmic randomness is the idea that there's no short description of the thing that can be given. So it's a big question. Is there, in fact, algorithmic randomness in the universe? And my friend Greg Chaitin, who is one of the inventors of algorithmic randomness back in the 1960s, and I have been having a running discussion about, is the universe really like pi, that is intrinsic randomness generation from my kind, where there's a simple description, but the digits once generated seem random, or is it like a thing that Greg Chaitin calls capital Omega, which is something which is algorithmically random, which cannot be generated by any process started from a short description. It can't be explicitly generated by any computational system, Turing machine, whatever, starting from a short description. So that's kind of the question, is the universe like pi or omega? Well, up until a couple of years ago, I would have said, well, I think it's like pi, but I'm not sure. Now that we've done our physics project, and we've launched our physics project, I think it is absolutely plainly the case that the universe is like pi and not like omega. That is, that there is underneath an intrinsically a simple description which is being run and generating through computational irreducibility, generating through intrinsic randomness generation, generating apparent randomness. Now, in the end, the phenomena that we see in the universe at the level that we typically observe and perceive things, the fascinating thing in the physics project is that we have kind of gone above that level of intrinsic randomness to see regularities that sort of cut across the intrinsic randomness in the same kind of way as there's sort of this randomness of molecules bouncing around in a gas, but we see nevertheless the fluid dynamics in the gas at a larger scale. And it's the same thing, I think, with the universe, and that's sort of a feature of the physics project. But I think this idea of intrinsic randomness generation that I sort of posited to be something that was important in many systems in nature, I think it's the case that one of the systems it's very important for is our whole universe, and that there is intrinsic randomness generation rather than algorithmic randomness, where the randomness is in a sense burnt in from the beginning, where you have to say the original description is very complicated, is very random, is very long. What I'm saying is actually the original description is very short. It's just the computational process of evolving the universe that makes, through intrinsic randomness generation, that makes something effectively random. Well, one of the consequences of intrinsic randomness generation is that experiments that are done that produce randomness, like Rule 30, should be able to be done repeatedly, and the experiments should be repeatable. And that's a weird thing, because usually when you think of randomness, you say, oh, it must be random from the environment, it must be random from something else. It'll never be the same the second time I run the experiment. But intrinsic randomness generation says it should be the same. And indeed, there is some evidence in experiments, although people have been loath to publish them because it seems so weird that, how could this possibly be right? That even in things like in fluid dynamics, where well-controlled experiments can seem to show apparently random patterns of behavior, even though but do so repeatedly. So you can run the experiment a second time, it'll show the same apparently random pattern. Okay, well, continuing in chapter 7, I've talked about this idea of these three different sources for randomness, and I argue that intrinsic randomness generation is a critical source for randomness in many actual systems in nature. In chapter 8, we'll see that developed in more detail for particular actual systems in nature. But here I'm just sort of talking about the principle of these three different sources, the environment, the initial conditions, and intrinsic randomness generation, and talking about the importance of intrinsic randomness generation. Okay, chapter 6 is a chapter that, section 6, is something which, in the light of the physics project, has become a bit more important than it seemed to be in any obvious way in the NKS book. So the question is, one of the phenomena we see in nature is continuity. We see that things appear to be apparently continuous, like space, like fluids, things like that. How does that happen? And how does one go from intrinsic randomness to large-scale continuity? And so I talked about that. This is a really kind of a survey section because many of the things in it are quite are sort of known in some way or another. This is about random walks, saying that even though the individual walks are random, you build up this Gaussian distribution of final configurations. Really, this section was a section that was intended to be sort of a foundation for things that we'll talk about later in actual phenomena in nature. So one of the things here is talking about the fact that the central limit theorem, the fact that even though the microscopic details of how a random walk works, how much it can jump on each step and what correlations there are and so on, even though those microscopic details might change, still the overall distribution of results, the continuum limit will be the same. And that's a feature of the central limit theorem in statistics. And that's one of the sort of symptoms of this very general phenomenon that continuum limits can be quite insensitive to the details of what's underneath, so long as what's underneath is effectively random. And that's something that will be important in the physics project and so on. So I'm talking here about two-dimensional random walks and just showing some pictures of the kind of the outer limits of where two-dimensional random walks get. This is another example, which I've actually just been studying recently again. This is an aggregation system where it's again based on sort of randomness, where you start off with a black cell, and at every step you add a black cell randomly at some position on the outer boundary of this system. And you see that in the end you get this continuum-like structure. It's almost circular, but not exactly circular. But it has sort of a continuous limit. This is a case of a generalized aggregation system. I've just been studying these again recently in the context of multi-way systems, actually, because what we here talk about as randomness, you just randomly add a cell to the growing surface. When you think about things in terms of multi-way systems, you could say, what are all the possible ways to add a cell to the surface? And how does that, and what can happen? But these are cases of generalized aggregation systems. I don't think these have been studied before, where one looks at something where one says, add something to the surface only if the local configuration doesn't involve more than some number of black cells. And so you get something which has holes in it rather than just being a continuously filled in system. So I talk about this is a case of a completely deterministic system, which again produces apparently continuous behavior. This is just a two-dimensional cellular automaton. In fact, I showed a small example of it in chapter 5. And if you started off here, it will grow into this pattern that seems to have a continuous boundary. It's almost a circle, but again, not exactly a circle. So that's an example of where one's generating continuous behavior. Even though this is a square grid, you get an approximately circular pattern of behavior. Okay, this is another example. This is a cellular automaton that has kind of domains, a two-dimensional cellular automaton, which has these kind of domains that sort of blob around with apparently continuous behavior. And this is showing kind of the micro details of how that works, because it actually has little digital pieces running around that on average give you that kind of continuum behavior. But you can kind of see the digital structure underneath. Okay, so in terms of origins of continuity, talk about a bunch of different kinds of systems here. I talk about that circularity in the code 746 system and the fact that its slight deviation from circularity is seen there. Similarly, in diffusion limited aggregation, a slightly more complicated case. This is about those generalized aggregation models where you can pick different rules for whether you add a cell around the boundary. These things have not been studied in great detail. I've just been studying them again, because one of the interesting things is that, for example, here, you get a system which seems like it gets stuck after 6,800 steps. It seems like there's no place to add anything on the boundary. It's kind of like one of these long halting time problems. Turns out when you look at this particular one as a multi-way system, yes, many branches get stuck, but there are still some survivors. There are still some ways that with the appropriate choice of random numbers, so to speak, the system can keep on growing. But those are examples of more complicated aggregation systems. Oh, that's a good idea. Looking at Oh, these are 1D versions. I should show that actually in the thing that I've just been working on for these aggregation systems in these multi-way versions of aggregation systems. Let's see. I talk about yeah, this is the theory of isotropy in systems on lattices, and it has to do with well, there's a kind of a nice group theory way of understanding under what circumstances, what kinds of things can be how isotropic on lattices of different kinds. You know, I realized that these things, they should go down and across, but they actually go chink, chink, left, right. So it's a bit confusing. Okay, this is talking about the domains in that system that has sort of continuous evolution towards different sort of continuous domain boundaries. Okay, so that was a little bit on the origins of continuity from systems that are initially discrete, and how you can get things like circular patterns of behavior even when you've got discrete deterministic evolution according to a cellular automaton rule on a square grid. Okay, the other way around is discreteness. How do you get discreteness in large-scale discreteness in these systems? So here's an example of a cellular automaton. This is rule 184, where depending on the initial conditions, it doesn't care about the details of the initial condition, but it does care about the overall fraction of black cells. If it's more than 50% black, it'll end up with left-moving black stripes. If it's more than 50% white, it will end up with right-moving white stripes. It's a phase transition. If you just have just a tiny bit less than 50% black or a tiny bit more than 50% black, there'll be a discrete transition from it being black to it being white, white to it being black. Actually, this particular rule turns out to be sort of a minimal model that's used for road traffic flow, and this story of the transition is the formation of traffic jams. But this general idea of phase transitions, the idea that just like, you know, when you have water below 100 degrees centigrade and you heat it up, it'll suddenly all turn to steam, or you cool it down again, it'll suddenly all turn to water. That discrete transition, even when you make a continuous change of a parameter, is a so-called phase transition. It's an important phenomenon in physics. It's an important case where continuity leads to discreteness. And the best minimal example of that is something that you see in a cellular automaton here. It's something where people were a bit confused because in standard statistical mechanics, you don't see phase transitions in one-dimensional systems because of the reversibility that you put into standard statistical mechanics. Without that, you can perfectly well see phase transitions in one dimension. And in fact, the sort of meta model of phase transitions, I think, is very clearly illustrated by this particular system here, which is a solidly one-dimensional system. So this is a case, another cellular automaton, where below 50% black cells, the thing eventually is all white, and above it's all black. And what you see right at the 50% point is you see this kind of nested pattern of of big triangles that are going to turn into black and big triangles that are going to turn into white. And that's a phenomenon in critical phenomena, in the theory of critical phenomena. That's a characteristic phenomenon that is seen at the critical point, right at a phase transition. You see this, the system is sort of unable to make up its mind. Should it go to one phase or the other? And so you get these kind of bubbles of progressively larger bubbles of each different phase nested within each other. And that's what you're seeing with great clarity in this particular cellular automaton. So this is another example of that in 2 dimensions, where it's rather just another case where you see below 50% black, it all goes to white. Above 50% black, it all goes to black. What's this like? Well, you can kind of think about a mechanical system where you just say there's a kind of a track like this. And if it's slightly to the left of that, it goes down to the left minimum. If it's slightly to the right, it goes to the right minimum. And that's kind of the way that works. And so this idea of discreteness arising from continuity is a feature. It's something that has sort of was quite a mysterious thing in physics, although we see in this sort of meta model, it's very direct how that happens in this case. In physics, it's seen in phase changes between solid, liquid, gas. It's seen in demagnetization. It's seen in lots of other kinds of things. Let's see. Here I talk about one of the sort of the minimal model for phase transitions that's used in physics, the Ising model. The Ising model has an array of cells, and each cell has a spin that's either up or down, and it has an energy function that says that if the spins are locally all aligned, it'll have a lower energy. If they're locally all misaligned, it'll have a higher energy. That's what leads to ferromagnetism, is when the low energy state is the one where all the spins are aligned. So the question is, how does that work in the systems we're talking about? Well, actually, you could make a cellular automaton that represents kind of the flippings of spins. But let's see if I'm talking about that here. No, here I'm just talking about okay, those are actual dynamics. So if you ask about the Ising model and you say, what is the magnetization? To what extent are the spins all aligned? And what is the energy of the system? You can simply look at all possible configurations of the system, and you can ask the question, if you look at above some energy, what is the distribution of configurations? And at a high energy means that these spins are mostly not aligned with each other. So that means that most high energy states will not have an overall magnetization. And what you see directly in these plots, where I'm just plotting all possible states of the system, and the darkness level is the number of states that are at this particular position with respect to energy and magnetization. And so what you see is when the energy is high, the magnetization is zero for essentially all the states. When the energy is low, the magnetization is either +1 or -1, and it can be one or the other, but nothing in the middle, because the low energy states correspond to ones where all the spins are aligned. They have to be all either up or all down. And so this is essentially the phase diagram that you get purely from this combinatorial counting of states in the system. This is the phase diagram that you get. This is essentially the Curie point of the system, the place where if you heat it up, so you increase the average energy, the magnetization goes to zero. You cool it down, it spontaneously magnetizes because it has to go on one branch or the other. So it's rather elegant that this works out just by looking at this pure counting argument. This whole system was solved exactly in 1944, and you can kind of do the analysis here. The exact solution comes in the case where you say that you're looking not at this all possible states of the system, but you're saying, let's look at states of the system weighted with e to the minus beta times the energy, where beta is the inverse temperature. So you're looking at that particular weighting, and you're saying, with that weighting of states, what does this diagram effectively look like? And an exact solution was found to that. Okay, so one of the things that looked at is, let's imagine that you are looking, so in the usual version of statistical mechanics, you have the so-called canonical ensemble, where you say you've got this system and it's in contact with a heat bath, and the heat bath is kicking it around, but kicking it around with a certain distribution of energies that's given by the c to this minus beta h function, the Maxwell distribution. But you can also imagine a microcanonical ensemble where you take the system and you fix its energy, and you say, how is the system going to flip around based on some dynamics of how the spins move? There's a common model named after Roy Glauber, who I knew back in the day, who just suggested you take these spins and you just randomly flip a spin using some sort of external source of randomness. But you can also, now that we know about intrinsic randomness generation, you can also just say, well, what about if the spins are flipping according to a deterministic rule? What if there's just a cellular automaton rule that flips the spins? Well, you can do that, and then you can ask, how, given that you start from a certain energy state, will you see the what will you see in terms of magnetization? And indeed, you see all the right results. And so this is a case where, even though the dynamics is deterministic, they make enough of their own randomness, so to speak, that you see the same results as you would if you picked all possible configurations at random. So one of the big ideas in statistical mechanics is the notion of ergodicity, the idea that eventually the system will visit all its possible states, maybe even with equal probability. And if it does that, then you can replace averages over the ensemble, averages over all possible states, with averages over time, because if you wait long enough, it will just visit all the states. And so the question is, when you actually have real dynamics, how quickly do you get something which is a good approximation to having visited all the states? And what this is saying is that even the simple cellular automaton does a good job of picking out states randomly enough that with respect to these statistical measures, it will seem to be something that is consistent with ergodicity, so to speak. Okay, I talk about phase transitions here. And very simple type of phase transition, percolation. These are a little bit more detail there. This is just another example of how you can get discreteness from a continuous system. If you say, and this is something biology uses quite a lot, if you have something where you have a sine wave, and wherever it's above zero, you get one result. Wherever it's below zero, you get another result. That's used in the Hox genes, for example, in sort of tissue differentiation in organisms and so on. And you can get very elaborate patterns here because you can have something where, for example, if you have multiple sine waves at different angles, you can end up with a very, very complicated looking pattern of where you get plus and minus regions in the system. Okay, all right, another section of chapter 7 is, again, remember, we're going through sort of mechanisms that are used in nature. Another mechanism is constraints. We've talked a lot about how simple rules can generate certain behavior. We talked at the end of chapter 5 about things like tilings, where instead of specifying a rule for evolution of a system, you're just specifying, you've got these tiles, now I just want to lay them down in such a way that you satisfy certain constraints about these tiles. So this is a general question of what does it mean when you have a bunch of constraints and you're trying to satisfy these constraints? So what is this? To remember this. Okay. So this is a tiling problem, the same tiling problem we used in chapter 5, but now we say, let's just throw down tiles at random. Let's just look at all possible configurations of tiles and ask, how often do we just by chance satisfy the constraints? And so here we're seeing the fraction of possible patterns, what percentage of squares violate the constraints. So what we're seeing here is that on average, about 70% of the squares violate the constraints in a 10 by 10 array. So if we just pick the things at random, they will not satisfy those constraints. Now we're asking this is sort of a genetic algorithm or an iterative algorithm or a metropolis algorithm or a Monte Carlo algorithm, something like this. We say, let's start from something where we randomly laid down the tiles and let's keep flipping tiles so that we're doing progressively better at satisfying the constraints. Do we ever reach the final place where we've satisfied all the constraints? Or do we get essentially stuck in a local minimum? So this is showing what happens when we try and do that. And there's the exact result. And there's what we get. And as you can see, we don't get terribly convincingly towards the actual result. We get some things which locally look a little bit like the exact result, but this is the only exact result and its immediate rotations, this kind of rigid pattern. And we just don't get to that by sort of progressive improvement of this original random pattern. And so I'm talking a bit more about progressive improvement and the importance of that. This is something which in the modern world of neural nets and so on is something that has become more important again, of asking kind of to what extent can you, by progressive improvement, reach some complicated, satisfy some complicated constraint. So I'm talking here about, again, various kinds of constraint satisfaction. Yeah, these are cellular automata for which this pattern on the right would be invariant. The cellular automaton would leave that pattern invariant, but in fact, it kind of changes the pattern when you run it. And this is showing what is the final state from a bunch of cellular automata that have the feature that they always leave. If they reach this state, it will be left invariant. But what do they actually do? And some of them sort of get somehow closer to that state than others do. Okay, so a more real world example of this is you have a bunch of circles and you kind of crush them together and you say, what pattern do you get? Well, in the case of circles, you crush them together, you always get this hexagonal pattern. In the case of spheres, the densest packing is this kind of Kepler packing, but that's not what you get when you just sort of randomly throw spheres together. They get jammed. That's why you have to kind of take, I don't know, coffee beans and sort of coffee, ground up coffee and sort of knock it a bit so that you get the grains to settle in a different way, because they have stuck themselves in a configuration where they are not as close packed as they might be. But in any case, the question that I was curious about, very curious about in the NKS book is, with the constraint of just having the circles as dense as possible, what kinds of patterns can you get? Can you get complex behavior, for example, just from constraints? And so this question of, if you take like different sizes of coins in a certain ratio and you say, what's the closest packing? If there's just one size of coins, the closest packing is hexagonal. But if there are two sizes of coins, it's simply not known for most ratios of coin sizes what the closest packing is. And in the NKS book, I did some experiments on that. And these are cases where these are particular algorithms for trying to find the densest packing. And what you see is that the densest packing, at least as found by those algorithms, is definitely not a very organized regular packing. And it could very well be the case that for some ratios of sizes, the densest packing is something very complicated. It's sort of a something which is a non-periodic tiling. It could have all kinds of features. It's just not known. But I was curious in writing this, whether there might be a very easy way to generate complex behavior from constraints by just using packing of unequal sized circles. Still don't know the answer to that. So all sorts of different things discussed here about iterative improvement of constraints and so on, about circle packings, and what on earth are these? Okay, that's the procedure I was using there. These are, if you just have a single circle in the middle that's of an unequal size, how does that produce different patterns outside? And you see that even that single circle, that single seed, ends up with different closest packing patterns. There are particular cases where you know what the closest packing is. One typical example is where you can have some circles that fit into the interstices between other circles. This is a case of the Apollonian packing, where we do know what the limiting structure is, and we are progressively fitting smaller and smaller circles into the interstices here. And it's kind of an interesting mathematical problem, which was exactly solved, about what the limit of this Apollonian packing actually is. Let's see, talk about sphere packings in higher dimensions. That segues into all sorts of group theory and so on. I talk about Voronoi diagrams. That's you just lay down points and then you ask to draw a diagram where you make cells where things are closer to that point. You draw a cell of every point that's closer to that point than to every other point. It's kind of like the idealized sort of where do people shop? If there's a store in this place or that place, it's people who are closer to this store than to that store who will go to that one, and you kind of break things up that way. And there are lots of kinds of systems in nature that form this kind of Voronoi diagram structure. Okay, so I talk a bit about protein folding. I talk about that elsewhere as well. Oh boy, I keep on getting confused by the reading across versus reading down. Talking here about the sort of formal NP completeness, biologically motivated schemes for combinatorial optimization. That's essentially genetic algorithms and so on. Here I'm talking about sphere packings and the results that are known on sphere packings. Let's see. should be something here. Oh, okay, this is interesting. This is a case where you can actually make exact packings. So this is asking, again, a discrete analog of circle packing. You arrange circles, as many circles as possible, with a given diameter on a grid. So this is, assume everything's wrapped around. You're just putting down circles of a certain size. What's the best way to put down however many circles? This is 5 circles on a grid of this size, and eventually you're only fitting 1 circle here. But what you see is that the configuration, the optimizing configuration, is actually something that looks quite random. And actually, we have more data now on these kinds of discrete packings. Let's see. Discrete Voronoi packings. Okay. Oh, that's talking about cellular automata that can implement Voronoi diagrams. This is a one-dimensional cellular automaton where you essentially started off from a certain set of points, and they produce these kind of runners, and the runners run as far as they can until they collide with the runners from another point. And that essentially produces the Voronoi region for those 2 points. And you can do the same thing in 2 dimensions. This is kind of a progressive way to make a Voronoi diagram. Okay, this is an interesting question of, I think I talked about this elsewhere as well. This is the question of if you just throw together kind of deformable objects, in what configuration will they find themselves? And you end up with these rather complicated tetrahedra, 14-faced objects, which are the most common kind of packing. And you see that in biological cells. You see that in things that are sort of just thrown together with the formal object being squashed to be packed, as opposed to spheres, rigid spheres. This is deformable things. And there are questions about sort of optimization of that. And the most obvious kind of repetitive pattern does not, it turns out, give the optimal packing. And you don't get the most obvious object is not the optimal one. And there's more complicated ones that are the optimal ones. Again, complicated behavior, in this case, forced by constraints. So there's a different thing from the evolution to complexity. This is complexity produced by constraints. We already saw that in the tiling problems of that we saw in chapter 5. Okay, the final section of chapter 7 is about origins of simple behavior. What makes things be simple? Well, you know, there are lots of cellular automata that aren't simple, and even if you change their rules only a bit, they are still, you won't get to one that's simple. There are cases where things are simple. There are cases where everything dies out. There are cases where you average out the randomness enough, it will eventually blur out to nothing. There are cases of this phase transition where everything goes to black or white. There are cases where you get repetitive behavior. That's a form of simplicity. And there are cases where, like in Rule 110, you eventually get a repetitive background. It's repetitive. Even though it might start complicated, eventually it becomes repetitive. Now, so the forms of simplicity that are most common are uniformity, repetition or periodicity, and nested behavior. And so this is just recapping on things that we saw in mostly chapter 5 here, of systems that progressively subdivide and produce nested patterns as a result. And different cases, this is a case where, I don't show this anywhere else in the book, this is a case where you're making a nested pattern by this kind of progressively putting out feelers effectively that sometimes merge, sometimes don't. That's just a way to make a nested pattern. This is showing that even Rule 110 effectively makes a nested pattern when looked at on a large enough scale, even though it has extensive structure on a smaller scale. These are cases of cellular automata where you effectively have 2 domains, where this is sort of where in this domain, you have one background color, in this other domain, you have another background color. It's the same rule everywhere. But what's happening is that the initial conditions sort of randomly are members of each of these two domains. And as you evolve the system, these domains gradually merge with each other and they become larger and larger, and you get essentially this nested sequence of mergings that happens. So it's again kind of an example of simple behavior arising, even though the underlying behavior is quite complicated. So we've got all sorts of issues about, I mean, this is really the domain. Simple behavior is really the domain where traditional mathematical science has been at its strongest. So nesting was not something that really was well tackled by traditional mathematical science. Repetition, Fourier analysis, all the different forms of that, very widely discussed in that area. Okay, this is more ways of doing nesting. This is nesting parentheses. These showed up again very recently in my work on combinators as ways to visualize combinators. This is a bunch of parentheses, which are, whenever they are correct matched parentheses, they will be in some sense nested, and you can sort of plot out that nesting in a variety of ways, and you can see kind of the overall structure. Talk about self-organized criticality. This is a particular example of, again, yet another system. This is one which actually got very, very, very confused. It was about sand piles, and you imagine that you just have you drop a grain of sand on the top of the sand pile. You have a rule for if the slope is too great, the sand pile will avalanche down, and it ends up being a two-dimensional cellular automaton. And you can ask the question, well, what will happen in that case? And unfortunately, there was a lot of confusion in the literature because somebody kind of got wrong. Is it going to make 1 over f noise or 1 over f squared noise? They just got the calculation wrong. And so people were very excited it was going to make 1 over f noise, which is kind of an unusual form of noise and fluctuation. It just was incorrect. A simple, almost arithmetic error. So that was very, very confusing. But I did look, and people have looked subsequently in more detail at this, at a simple deterministic example of this that didn't have a lot of mystery associated with it, where you're simply looking at essentially dropping the sand in a way so that you grow according to this two-dimensional cellular automaton. And you can see that with this kind of scheme, and you're sort of going according to the cellular automaton until you reach a fixed point, then you're dropping another grain of sand on, and the runs of the cellular automaton are the progressive avalanches. And once that's worked its way through, then you're ready to drop the next grain of sand, and you're sort of driving the cellular automaton again. Well, it turns out, yet again, simple rule, complicated behavior, you get these complicated patterns that are produced in the sand, so to speak. I don't know whether this will again be an example of intrinsic randomness generation. I didn't really study it from that point of view. Actually, now that I think about it, I think I've actually seen this now in an example. In a place in Peru, actually, where there were very interesting sand dunes. I have to go back and look at those photographs. I'd forgotten that. That was something that 15 years after the NKS book came out, that was something that I saw, and I didn't properly connect this note to that. But in any case, this is showing yet again another example of where there is intrinsic randomness generation, and even though the system is completely deterministic, and even though the rule is very simple, the behavior is complicated. And I make about as far as I'm prepared to go in this book to saying that was all complete nonsense. I say the behavior once is fairly complicated, a fact which in the past resulted in much confusion and some bizarre claims, but which in the light of the discoveries in this book no longer seems surprising. Again, those are examples of slices, space-time slices through these kind of sand piles, showing sort of the way in which these avalanches happen. And let me see, is that everything here? I talk about much there. I talk about the fact that this notion of repetition is iteration in algorithms. Nesting is recursion in algorithms, and these are things that one talks about in algorithms and that's sort of, those are the same examples of simple behavior. Uniformity, repetition, nesting, those show up all over the place. And those are our best examples of regularities. And in fact, if we ask what are the generic regularities which go beyond that, that's a very interesting question, but we know almost no answers to it. And in chapter 10, I'll talk a little bit more about some of what we can say about that. But that's a case where we're asking, is there what kinds of simple behavior can actually occur? Okay, so recapping on this chapter again, mechanisms and programs in nature. What we see in simple programs is sort of a strong enough phenomenon that we can expect to see it not only across simple programs, but also across systems in nature. Big phenomenon is randomness, and these three mechanisms for randomness: randomness from the environment, randomness from initial conditions, and intrinsic randomness generation. And the argument that intrinsic randomness generation is a very important and common phenomenon that is something that requires nothing from the outside world. It is just intrinsic to the system itself. Talking about sort of different kinds of generic behavior, continuity became much more important with the physics project, origins of discreteness, phase transitions, and so on. Whether you can get what kinds of behavior you get by satisfying constraints. Again, even with simple constraints, you can have very complicated behavior. That's, again, the big message of the NKS book. And finally, how does simple behavior arise and what kinds of simple behavior are common to see in systems? And again, that will reappear later in the book when we talk about the principle of computational equivalence and the fact that when you are out of the zone of these forms of simple behavior, you tend to be in the zone of maximally sophisticated computation. All right, so that's a walkthrough of chapter 7, and I think there maybe are some questions here, so let me try and address some of these. Let's see. Luis comments on permutations maintain entropy for sand in a sandglass, moving between configurations of the same entropy, yet it measures time properly. I think entropy is a very slippery concept. You know, entropy is the number of states of a system consistent with the constraints that you have put on the system or that you know about the system. So if you say, all I know about the system is I've got gas in this box, or all I know about the system is I've got gas in a box half the size, entropy is just asking, given what you know about the system, how many possible states of the system are consistent with what you know? It's not a statement about a particular state of the system. It's a statement about a constraint on the system and then asking how many states of the system are consistent with that constraint. It's something that kind of goes beyond the specifics of the system. It goes into the set of all possible states generated by the system. So I don't think there's an hourglass. The question of sort of how an hourglass manages to sort of keep accurate time, I think that's an example of something where it's the discrete granular flow that will have a lot of discrete features, but if there are enough discrete sand grains, there's an approximation to continuous flow. And we'll actually see in the fluid dynamics section of chapter 8 coming up next week, we'll see some examples of some things like that. Okay, 675 says, something is truly random, how can we be sure? Wouldn't there be an associated probability for discovering that it is truly random? Yeah, if something is truly random, the way you can tell if something is truly random is you can say, you say, there's no description of the thing shorter than the thing itself. Okay, how can you tell? Well, let's just try all the descriptions, let's say Turing machines. Try all the Turing machine programs which are shorter than the sequence itself. Now, the problem is that's something you can't do in practice because some of those Turing machine programs they'll flap around and they won't halt, and you don't know whether they're going to eventually produce the thing you're looking at by some very clever means, but it takes a million steps, or whether they're just going to go off and not halt. Now, you can kind of limit things. You could say, well, I want to know about things that are produced in less than 100 steps or something. Then you're kind of tweaking this question and you quickly segue into the sort of intrinsic generation of randomness. But it is true that there is this one method, which is you just try all the simpler descriptions and see whether you can generate the thing from something simpler. That's a foolproof but utterly impractical way to determine whether something is algorithmically random. Okay, so DSG comments about patterns being random. Yeah, I mean, these are slight abuses of words. I mean, one often talks about sort of patterns of black and white cells, even though it's sort of just an arrangement of black and white cells. And the question of whether that arrangement has identifiable sort of regularities or not is something one's kind of not addressing when one says pattern. One probably should rather say arrangement of black and white cells. Okay, so William is commenting in chaos, in sort of sensory potential initial conditions, the nearby states in phase space and the space of all possible states diverge exponentially. Let's see, but in intrinsic randomness generation, you can't narrow the phase space to the initial condition. Yeah, so what happens, and William is asking, is this like encryption? The answer is yes, it is absolutely like encryption. Intrinsic randomness generation is really a story of the encryption of the initial conditions of the system by the actual behavior of the system. The type of encryption, like Rule 30 or something, it's different from the types of encryption that are commonly used, although Rule 30 was something that I suggested as an encryption system back in the early 80s. It's something you could potentially use for that. But yes, that's what's happening in intrinsic randomness generation. Okay, so William is asking, does the appearance of randomness depend on the observer? And can we redefine states so that it doesn't seem random? Well, the answer is yes. If the observer knows that those digits are the digits of pi, the observer can, if that's burnt into the observer, if the observer is obsessed with the digits of pi, and you see this random sequence, you'll say, that's not random, that's the digits of pi. So it is a complicated story about the interaction between the observer and the system. It is really a statement, and I talk about this a lot in chapter 10, a statement about the fact that the observer is somehow is a generic observer, is a generic computationally bounded observer who can't kind of out-test the computational irreducibility that is producing that randomness. Again, this is a big subject of chapter 10, and we'll talk about that more there. Let's see. Alistair asked, did I do an exploration of spherical-ish shapes? No, I didn't. I mean, I got as far as circles, and that was pretty hard with different size circles. I looked at that. I did not look at different size spheres. It's just technically considerably more difficult. Didn't look at that. Good thing to look at. Question about irregular borders create perceived randomness. Yeah, I mean, again, chapter 10 is all about processes of perception and analysis. We'll talk a whole bunch more about the perception of randomness there. And Prutz here is commenting, encryption is defined as something you can decrypt afterwards. Does randomness generation fit the bill? Yes, the answer is well, you can certainly have examples where it does. So you can have a reversible cellular automaton, for example, that will take its initial data and grind it up and it will look random. But if you had every bit of the thing you got out, you could just run it backwards and get to the initial state again. And there are different sort of protocols for encryption, different mechanisms for encryption, which again have this feature that you can decrypt things again. I'll talk about this again in chapter 10. There's a whole section on cryptography and cryptanalysis and its relationship to randomness there. And I talk about the Rule 30 crypto system and other kinds of things. All right, well, I think that's about it. That was a survey of chapter 7 of A New Kind of Science. Next week, we will talk about chapter 8, which is entitled Implications for Everyday Systems in Physics and Biology and other places. It's a very fun chapter. Next week, by the way, just a logistical point, this will not be on the same day of the week. It will be on a different day of the week. Well, thanks for joining me for chapter 7 and look forward to talking to you again about chapter 8. And I think tomorrow we may be doing a live stream about archaeology of the NKS book, looking at some of the artifacts that went into the making of the NKS book. All right, thanks very much.